Okay, so we will come back again. So, in the previous lecture we have finished here that your 4 state variables are there, that delta omega r, delta delta, delta psi f d and delta v 1. So, it is actually x dot is equal to a x plus b u form, and if your mechanical torque input is constant, then naturally delta T m will be equal to 0, right. And this is the block diagram we have already shown there, that here we have all the 6 constant, that k 1, k 2, k 3, k 4 and k 5, k 6, right. And this is the exciter, and we will simply represent it by gain, but different type of exciters are available. In that case, it can be represented by different type of transfer function, but for the classroom purpose we will not consider that, we will take a simple gain. And similarly, for voltage transducer, this 1 upon 1 plus S T R, that later we will see that T R actually is very small. So, we will neglect this T R. So, simply we will take your what you call simply that delta E t, delta V 1 will be equal to actually delta E t, in the sense that T R, if T R is neglected. We will be back again for this transfer function, but before going to this thing, before coming again, so we will go to the next one. So, for thyristor exciter system, that we will simply represent a G X, that it is S is actually Laplace transform, but we will take a simple gain, right, and we will not consider the different version of exciters are there, then things will become a little bit complicated, right. So, we have seen that delta E t is equal to k 5 delta delta plus k 6 delta psi f d, that we have already derived, right. Therefore, the coefficient k 6 is always positive. So, earlier I told you k t, k 2, k 3, k 4 always positive, and k 6 is also positive, and k 5 may be negative, may be positive, right. Whereas, k 5 can be either positive or negative depending on the system operating condition, right, and the external network impedance, that is R e plus j x e. Now, next is effect of AVR, that is automatic voltage regulator we call, on synchronizing and damping torque components, right. So, from the block diagram, that is figure 30, we see that if we make delta V reference is equal to 0. So, I will go back to figure 30, right. So, this is just hold on, let me go down, this is figure 30. So, here that we will take, say for example, if delta V reference we set is equal to 0, and if we neglect your what you call that T R, then what will happen, that input to this, here it is k 6 delta psi f d and k 5 delta delta. So, here already we have seen that this T R actually is neglected, say it is 0, right. Then it will be input to this delta V 1 will be that we have made it k 5 delta delta plus your k 6, your from here it is coming. So, delta psi f d, right, and that is equal to delta V 1 is equal to your delta E t if it is neglected, right. And if we assume that delta V reference is equal to 0, then here it will be minus, and this gain is actually k a, right. So, it will be minus k a into this term, right, and from here it is coming k, this point it is coming k 4 delta delta, right, it is minus. So, it will be basically, if you look into that, it will be minus k a, right, into your k 5 delta delta plus k 6 delta f d bracket close, then again minus k 4 delta delta into k 3 upon 1 plus S T 3 is equal to delta psi f d, I mean this term delta psi f d. So, if you look into that delta psi f d for this case, how it will look like? It will be k 3 upon 1 plus S T 3, this thing, right. In bracket what it will come, that it will be your minus is here, because this delta reference is 0. So, here it will come minus k a, then these two term, right, that is your k 5 delta delta, k 5 delta delta plus k 6 delta psi f d, right, because psi f d is coming from here, then again it is your what you call the bracket close, then again minus k 4 your delta delta, because it is coming here. right, k4 delta then bracket close is equal to your delta psi f d, right. And this is actually this torque delta t has two component, one is due to delta psi f d, then further that k2 should be multiplied with delta psi f d, that is the whole thing, right. And another one is coming from here, that is k1 delta, right. I hope it is understandable to you, because you have all of you have studied the control system in third year or block diagram, same thing here, right. So we will go back to this thing, or what you call that. So that is why we are writing the same thing. From the block diagram figure 30, we see that delta psi f d, whatever I wrote there, that is your k3 upon 1 plus st3 in bracket minus k4 delta minus gxs, means this value actually is equal to k, right, divided by 1 plus str k5 delta plus k6 delta psi f d. But there, whenever I am writing this, I neglected tr. Later we will see that we will neglect tr, but here I have written it, right. So because tr is very small as compared to other time constant, right, but here I have written that k upon 1 plus str, that is gxs, right. So now upon simplification, if you simplify this, so it will become minus k3 k4 in bracket 1 plus str plus k5 gxs, and in denominator t3 trs square plus t3 plus trs plus 1 plus k3 k6 gxs delta, right. So now tr is not neglected till now, right. The change in air gap torque due to change in field flux linkage, that is delta Te due to delta psi f d will be kt into delta psi f d, because that if you go back to the figure 30, there you will see that your delta psi f d k2 delta psi f d and this side it is coming k1 delta that is delta Te. So delta T has two part, one is k2 delta psi f d, another is your that is k1 delta, right. So this is actually your the air gap torque due to change in field flux linkage, that is delta Te, and when I put in delta psi f d, that is your due to delta psi f d is equal to k2 delta psi f d. So this term should be multiplied by k2, I mean this term should be multiplied by k2. If you multiply it by k2, it will be minus your k2 k3 the whole thing, right. So therefore the constant k2, k3, k4 and k6 are usually positive. Actually k3 will remain constant for a system, and k5 may be positive or may be negative, right. The effect of the AVR on damping and synchronizing torque components is therefore primarily influenced by k5 and the gxs, that is a exciter transfer function, but here we will simply represent it by a gain, right, for the easy analysis. Now suppose following parameters are given for the system, suppose following parameters are given, say k1 is equal to 1.591, k2 is 1.5, k3 is 0.333, k4 1.8, T3 1.91 and k5 minus 0.12, k6 0.3, and for this case we have not neglected tr. For this case we have taken tr is equal to 0.02 second, right. Compared to T3, the tr is actually very small, we can neglect it, but for the time being we have retained it, we have not neglected, but later we will neglect it, right. And gxs we have taken again ka, h is equal to we have taken 3 second, and damping your coefficient kd we have taken say 0. Suppose these are the parameters are given for some analysis, right. So with this parameter, now part A, the first part, that is your steady state synchronizing torque coefficient. Now when we make delta psi f d, that s j omega tends to 0, then this will become minus k3 k4 as minus k3 into bracket k4 plus k5 ka divided by 1 plus k3 k6 ka into delta when omega is equal to 0. Now in this case, this is your what you call delta psi f d. So in this case here delta psi f d, if you make your s is equal to j omega and omega tend to 0, then in this case it will become minus and gx is equal to a. So it will become minus k3 k4 minus K3 K5 Ka, right, because Gx is equal to Ka divided by this term will go, this term will go, and it will be 1 plus K3 K6 Ka into that delta delta, right. So, here same thing, when we substitute all this, we will getting minus K3 in bracket K4 plus K5 Ka, right, and because Gx is equal to Ka divided by 1 plus K3 K6 Ka your delta delta. Now, therefore, delta Te, that component of delta Te due to delta psi Fd, because in that block two terms are there, delta T is equal to your K, your what you call that K2 delta psi Fd plus K1 delta delta. We are considering only that component due to delta psi Fd. So, delta T due to delta psi Fd is equal to K2 into delta psi Fd. So, multiply by K2, this delta psi Fd for omega is equal to 0. So, it will be minus K2 K3 in bracket K4 K plus K5 Ka divided by 1 plus K3 K6 Ka at into delta delta, right. Now, all these parameters are given, some parameters we have taken here, some parameters. So, what you do, all these available parameters you put in this equation, K2 value, K3 value, K4, K5 and K we do not know, right, K we are not putting, but 1 plus K3 K6 K, because here if you look into that Kd is equal to given 0 and Gx is equal to K, we will see the variation of Ka, right. So, if you substitute, then delta T due component due to delta psi Fd, one will get 0.06 K minus 0.9 divided by 1 plus 0.10 K into delta delta. This is equation 286. That means, this function is also in terms of delta delta, right. Now, and but this is function of K. So, K is a variable that is exciter gain Gx. We are not considering the transfer function for exciter. So, then things will become little bit complicated and not possible to do anything on the in the as a classroom exercise. It will create it will take long time, right. So, now hence the synchronizing torque coefficient due to delta psi Fd is, that is K's delta psi Fd will be 0.06 K minus 0.9 upon 1 plus 0.10 K. See, so this actually this one, this is that coefficient of this delta delta, this term delta delta, it is basically the synchronizing torque coefficient, because this is function of delta delta. So, this is your synchronizing torque coefficient, which is function of Ka. So, synchronizing torque coefficient value, it depends on the exciter gain Ka, right. So, that means just hold on. So, that means your this case we are writing that synchronizing torque coefficient in bracket, we are here we are writing delta psi Fd, because it is due to delta psi Fd is 0.06 K minus 0.9 upon 1 plus 0.10 K. This is actually equation 287. So, we see that the effect of the AVR is to increase the synchronizing torque component at steady state, right. So, so this is actually from that you can make it. Now let us see with K is equal to 0. If K is equal to 0 means constant EFD, right, because exciter gain says 0, that means nothing is there. So, in that case constant EFD means actually delta EFD is 0. So, there will be no effect for that your what you call for your exciter. So, when K is equal to 0, if you put K is equal to 0 here, then K's delta psi Fd will get simply minus 0.9, right, when K is equal to 0. So, this is actually simply you will get minus 0.9. Now, if the numerator that 0.06 K minus 0.9, if you set it to 0, suppose if 0.06 K minus 0.9 is equal to 0, you will get K is equal to 15, right. That means the AVR compensates exactly for the demagnetizing effect of the armature reaction. So, that means if you if you set this is equal to 0, that means Ks also will be 0, synchronizing torque component will be 0, because numerator if you set it to 0 for which K is equal to 15. So, in that case the AVR compensates exactly for the demagnetizing effect of the armature reaction, right. Now, suppose take some value when K is equal to 200. In that case, if you put K is equal to 200, say this is another case, if you put K is equal to 200, then you will get it is 0.529, that K's due to delta psi Fd is 0.529, and the total synchronizing torque coefficient is actually it will be K1 plus Ks delta psi f, this is 1.591 plus 0.529. Why it will come? That we know this that look at the, I am not going to the block diagram again. If you go back to figure 30, then there you will see that this delta Te is equal to your what you call K2 delta psi fd plus your K1 delta delta, right. So, in this component, actually this component is your what you call this delta psi fd due to your K2 delta psi fd, and this one we are representing, just hold on, this one, just hold on, this one we are representing by this component, your what you call that delta t component due to this function, right. And whenever we are putting that K2 is equal to your K is equal to 200, we are getting K's 0.529. So, this term, if you look into this term, this is due to delta psi fd, just hold on, such that your understanding will be clear. So, this is a function of delta, and when you put Ka is equal to say 200, you are getting this value actually how much we got 0.529, right. So, this is actually due to this delta psi fd term, plus one more term is there. So, that is why we are writing that Ks, right, that is your delta psi fd is equal to 0.529, right. But we know that delta t has two terms, that is one is K2 delta psi fd, that is this term, one is K2 your delta psi fd, and another is K1 delta delta, right. This is figure 30, from figure 30 you know that. Now, K2 delta psi fd actually basically this is the function and delta delta. So, we get if we put K is equal to 200, then you will get 0.529. So, that means this term actually becoming 0.529 delta delta, right. And another term is there K1 delta delta. So, basically let me clear it. So, basically your delta Te is equal to your this term 0.529 delta delta plus K1 delta delta, right. Now, question is that K1 value is given, that here K1 value is given, just let me go back to this thing, K1 is given 1.591, right. That means I am writing here only, that means your delta Te is equal to your 0.529 delta delta, this is due to delta psi fd, plus this K1 is there 1.591 delta delta, that means it is 0.529 plus 1.591 delta delta, because K1 is given the right. So, if you add this up, so it is basically your synchronizing torque coefficient is increasing, right. So, that is why we have written here, that is why we have written here that Ks is equal to your K1 plus Ks delta psi fd, right, and total is your what you call 2.12 per unit torque per radian, this is the its per unit value, right. So, basically Ks is a dimensionless quantity. So, that is why this K1 plus Ks delta psi fd, I do hope that meaning of this you might have understood, right. So, little bit of your what you call little bit of study is required to get into this, right. So, that is why each step I wrote for you, such that there will be no confusion, and when you will see this, you just open figure 30, because all notes will be provided to you, right. So, this is actually that case. So, here we consider a case now with K5 negative, negative or positive, right. Now, with a positive K5, it is actually now if it is a K5 is positive, whatever we have seen there, it is K5 was negative. Now, if you see K5 is a positive, the AVR would have an effect opposite to the above. This is an exercise for you. Whatever value is given for K5 here, I think minus 0.12, I think it is, right. Whatever is given, that K5 we have taken minus 0.12, this is whatever effect we have seen. I will request you try for K5 is equal to 0.12 positive 1, and just see effect is just opposite or not, right. So, just you have a look, this calculation you will do it as an exercise. So, this thing, just hold on. So, the ABR would have an effect to the above, that is the effect of ABR would reduce the steady state synchronizing torque component. So, you can see that this value or what you call this value may become negative. If you take K5 positive, this value may become negative. It may not be the exact value, but or maybe exact value, it depends on the parameter, but it will be negative, not positive. So, if K5 is negative, it actually increases the synchronizing torque coefficient. If K5 is positive, it depends on the system parameters, right. So, if it is if you put K5 suppose 0.12, this value may become negative. It may not be 0.529, but it may be negative. So, hence if you just make the sum, so it will be your what you call, it will reduce, right. So, this is an exercise for you, just a simple thing, just you will put it and see it. I did not do it here, right. So, next is B, damping and synchronizing torque components at the rotor oscillation frequency. Now, suppose when S is equal to j omega, when S is equal to j, in this equation, just hold on, in this equation you put S is equal to j omega, right, and put all the values of K1, K2, K3, K4, K5, K6, all the values you put here, and Gx is equal to Ka, and put S is equal to j omega. So, if you do so, then your function will look like this. So, this then delta psi FD will become minus 0.6 minus 0.333 K5 Ka, because Gxs is equal to Ka minus 0.012 S divided by 0.0382 S square plus 1.93 S plus 1 plus 0.1 K delta. This equation is say 288, right. Now, and delta T due to delta psi FD means that is it is actually K2 multiplied by K2. So, mathematically this one is equal to K2, I am writing over it, K2 delta psi FD. So, this expression is delta psi FD multiplied by K2, and K2 parameter K2 we have taken 1.5, that is why it is multiplied by 1.5, right. So, if you multiply this, so delta T due to delta psi FD, right, is equal to 1.5 into the delta psi FD, that is the whole term, into delta. This is equation 289, right. Now, let us assume that rotor oscillation frequency say is 10 radian per second, that is 1.6 Hertz, right. So, with S is equal to j omega is equal to j10, if you take omega is equal to 10 radian per second, so omega is equal to 2 pi f, so from which we will get the frequency is 1.6 Hertz, right. So, our actually interest is generally in between for this what we call rotor oscillation, our main interest is it is in between 0.2 to 2 Hertz, right. So, it is if it is 10 radian per second, say that is 1.6 Hertz, and S is equal to j omega, omega is equal to 10. So, j10. So, what you do here, you put S is equal to j10 and simplify. If you do so, it will come that your minus 0.9 minus 0.5 K5 Ka minus 0.1 j 0.12 minus 2.82 plus 0.1 Ka plus j 19.3, right. So, K5 value has not been substituted yet, but rest of the values have been your what we call have been substituted here, right. So, this is equation 290. This is delta T due to delta psi FD, this I have explained before, right. Now, suppose now with K5 is equal to minus 0.12, whatever value we have taken for K5, say it is minus 0.12, and K is equal to say we have taken 200, right. So, in this case if you put K5 is equal to minus 0.12 and K is equal to 200, then you will get delta T component due to delta psi FD, that is 11.1 minus j 0.18 divided by 17.12 plus j 19.3 delta delta, right. So, if you just numerator and denominator, if you multiply by this and simplify, it will be like this. I mean this term, only this term you can write like this, that is 11.1 minus j 0.18, right, into 17.18 minus j 19.3, numerator and denominator you multiply by 17.18 minus j 19.3, and if you multiply this one also 17.18 plus j 19.3, then 17.18 minus j 19.3, numerator and denominator you multiply by this, then you will, then this one you multiply, and this denominator, this term basically will be 17.18 square plus 19.3 square, right. So, then you simplify and you simplify. If you simplify that, then you will get that your delta t delta psi f d will be 0.2804 delta delta minus 0.3255 into j delta delta. So, this is actually, this part is equal to actually synchronizing torque component, and this is the damping part, because j delta delta. Earlier we have seen, no, something I asked you that it is in phase with delta omega and it is 90 degree out of phase with delta delta, that is you have seen in your phasor diagram, but this torque component also we define like this, particularly this thing, right, it is quite interesting. So, that means that the effect of the AVR is to increase the synchronizing torque component, because this term is positive, this term is positive, because it is because it is function of delta delta, right, and decrease the damping torque component when K5 is negative. So, when K5 is negative, this coefficient actually is negative, it is minus, right, because damping term is function of j delta delta or in phase with delta omega, we will see later, right. But I put in the previous lectures that you put in the forum that why it is so, and but just now you will know after this numerical, and this is your 0.2804 delta delta, this is your synchronizing torque coefficient, this is positive, right. So, right, when K5 is negative, we have taken K5 is negative, right. So, therefore, net synchronizing torque coefficient is K1 plus Ks delta psi f d, that is 1.59 plus 2.2804, because that if you go back to the figure 30 again, that you know this, that delta t has two component, right, that is one is coming your K2 delta psi f d and another is K1 delta delta, right. But due to your delta psi f d, the synchronizing torque component is this one, that means this one actually 0.2804 delta delta, and K1 how much we have taken, I think 1 point, just let me see, that your K1 data we have taken 1.591. So, it is actually basically what is happening, that your delta t actually it is coming 0.2804 delta delta delta, because this is due to your delta psi f d, K2 delta psi f d plus 1.591 delta delta. So, basically it is 0.2804, right, whatever it is, plus 1.591 delta delta. If you add this, this is the effective synchronizing torque component, right. So, because this torque is in phase with delta delta. So, this is actually coming K1, we are writing Ks delta psi f d, because this term we define that Ks, the synchronizing torque component due to delta psi f d, right, that way, that is the meaning, is equal to 0.2804. So, that is total is coming 1.871 per unit torque per radian, because this is a dimensionless quantity, because this is per unit torque means dimensionless, radian also dimensionless. So, it is a dimensionless quantity. Thank you very much, we will be back again.